You can kick us off today,
Oh,
yeah.
I will. I will. Thank you, sir. While you have a little sip of your tea. Um,
Our maiden voyage. It's so bad. That
oh,
was so bad. But I was thinking, what rhymes with void?
you have a knack of just scraping puns out of absolutely anything.
I never get gold, but I never quite get like rubbish. I
Yeah,
just get I think there's something.
yeah.
There's something, there's
There's
like
always something
a
there.
little nodule or something there, isn't there?
Yeah, yeah.
Lauren, sorry. You go for it. Go.
I feel like you've stolen the limelight here.
Well, it's not
Anyway,
the first time. But the thing is, you are doing this once in a blue moon, aren't you?
all right. Let's
And
kick this off.
you're doing this once in a blue moon.
Yeah, I'm not giving you
The
the
reason I,
space.
and the reason I say that is because our episode today is on the
Look at him.
moon.
He's trying to steal the intro from me. All right. Welcome to the core of everything. Thanks so much for tuning in again. This week we
Mooning in.
are.
That's
So where I
carried
can
on.
mute
Sorry.
you or
Thanks very much for
something.
tuning in. Sorry. Yeah, go on.
Welcome to our episode. This week we're talking about the moon, which is the fifth largest natural satellite in our solar system, and it's the second densest after Jupiter's Galilean moon Io. We think it formed from an impact event about 4.5 billion years ago, so soon after the Earth formed, where an object called Theia smashed into the Earth and sprayed out a load of material that stuck together to form the moon. Now, the moon's actually moving away from us about 3.8 centimetres per year, and it has effects on the Earth, both the tides as well as actually causing some of the rocks on the Earth to move by several centimetres because of its gravitational pull.
Isn't it true that it's the Earth, the moon has this constant gravitational pull on the oceans and the tides, but it's the Earth that moves around the bulge of the water. That's why we get tides, right? It's not the moon's dragging it in and out. The moon is
Oh,
keeping the
interesting.
bulge, and the Earth is moving around that bulge.
Yeah, I guess that makes sense. It's like effectively rotating within this outer skin.
Exactly. Yeah, exactly.
Yeah.
Yeah. So that's why the tides come in and out.
Hmm. Wow. So obviously, like the moon is our nearest kind of natural celestial object, and because of that, we've explored it. So we had the moon landings in 1969, and then the last time we went was Apollo 17 in 1972. But there are plans to go back with the Artemis missions, and Artemis 3 is the kind of the first mission which will go back and land on the moon, and that's planned for 2026. And this is all surrounding a target of creating the Lunar Gateway, which is effectively this space station that's a collaboration between NASA, ESA, JAXA, that's Japanese Space Agency, CSA, Canadian Space Agency, and the United Arab Emirates Space Agency to create this lab that gives us access to the moon and beyond. And it will be a communications hub, a laboratory, and a habitation module as well. So the moon's an
On the
exciting
moon?
place. No, it will be in orbit around the moon and provide access to
Wow.
the moon.
Well, like a petrol station.
Yeah, effectively. Yeah.
Amazing.
Refueling station. But before we get into the moon, I just wanted to highlight a couple of things from an earlier episode that we did on ancient rocks, because there's actually a little bit of debate around some of the things that we said, and so I wanted to highlight that. So one of them was, it's about around these rocks from Nouveau-Guituk Greenstone Belt, which is in Quebec in Canada. And we mentioned a couple of things. So one of them was that these rocks contain some of the earliest fossils from about 3.7 billion years all the way up to 4.28 billion years old. This was in the paper by Dodd et al. 2017. And they suggested that these were tubes and filaments made out of hematite that represented microfossils. But there was a paper published by Greer et al. In 2020 in Lithos that suggested that these rocks that are older than 3.5 billion years from the Eoarchean, that came from sedimentary protoliths, so the previous rock before it was metamorphosed. These rocks are too deformed, too metamorphosed, heated, pressured, recrystallized to be able to preserve any kind of microfossils. So they suggest that actually these microfossils, they wouldn't be able to survive in these rocks, and that the features that they found, so various kind of associations between minerals, quartz, hematite, things like this, they could be non-biological as well. And one of the things they found, or that they were particularly looking at, were jasper lights. So this is where you got layered jasper, which is a type of quartz, and hematite, a bit like the banded iron formations, where you got these kind of alternating coloured layers. And it was the Dodd paper suggested these are the phases that contain the fossils, but actually the Greer paper suggests that these jasper lights are post-deformation, so they've come in much later because they're structurally discordant, so they don't kind of fit with the structure of the metamorphism that you see there, suggesting that they're not primary, but have probably come from hydrothermal metamorphism later on. So a few questions around that, really, still a bit of debate.
So we're saying that the rocks have been cooked too much or deformed too much for them to be representative of the original rock before it got deformed.
Yeah, and that
it's been changed too much by heat and pressure.
Yeah, and even the kind of the signatures of what were thought to be fossils might not be fossils.
Right. So they've been overprinted by something younger.
Yeah, but they might not have even been there in the first place.
Right. Well, yes, exactly. Yeah. Okay.
It could be kind of a false signature, effectively. And actually, even the ages of these rocks is debated. So there was a paper by O'Neill in Science in 2008 suggesting that these rocks are up to 4.28 billion years old. And we talked about samarium and neodymium isotope systematics, which is all very confusing. I can't fully get my head around it, but there was a paper by Caro et al. In 2017 that were highlighting that they'd found like an anomaly in these isotope systematics. But actually, the Caro paper was suggesting that rather than representing an initial age of these rocks, that it was probably a kind of geochemical inheritance in these plutonic rocks. So basically, you've got magma chambers below the surface, and they're inheriting signatures of these isotopes from different systems, which is kind of throwing things off a little bit. And actually, what you think might be ages aren't kind of the true ages. Bit of debate around that.
For sure. And I do think that a lot of times when you talk about rocks that old, it's far more accurate to use crystals rather than bulk rock samples, because you have this idea of overprinting, whereas some crystals might come from the original rock before it gets deformed. And we were talking about zircons in the Ancient Rocks episode, because zircons are very, very resilient to deformation. And so they were able to record sort of environments or at least their ages and haven't been overprinted subsequently, which is so that they're much more accurate.
And it's the importance of looking at the whole geological context as well. You know, the Caro paper looked at some kind of chemical sediments interleaved within these rocks, and it was suggesting that they were younger rocks, which kind of changed your whole perspective. So yeah, I hope that maybe clears things up or makes the debate a bit more complicated.
I think it makes it more complicated, but it's good to throw a spanner in the works, isn't it?
Yeah. On to the moon.
I think we should start talking about the geology of the moon. So originally when the moon first formed, it was much closer to Earth, and it was it's believed to be this molten ocean. Now you're going to talk about something similar later in the episode, but it's believed to be this molten ocean. And the general idea is that due to the gravitational pull of Earth, it had these sort of tidal forces that deform the moon into this ellipsoidal shape. And the moon is composed of the highlands and the lowlands. And the lowlands are composed of mare basalts. Mare basalts are products of volcanic processes on the moon.
And these are filling in like basins and impact craters.
Right. And the mare basalts represent basically seas of magma, and they predominantly make up the near side of the moon. There's only a few percent of the far side that have been affected by volcanism. So the far side is a lot more highlands than the near side.
And the reason they're called mare is because mare is the Latin word for oceans or seas. So ancient astronomers thought that they were liquid oceans.
And they infill, as you said, impact basins. So 3.9 billion years ago, there was big bombardment by large asteroids, creating huge basins on the surface of the moon. So like a basin is, a geological equivalent of a washing up bowl or something, isn't it? Magma rose from the moon's interior, and it filled these basins with lava. They crystallized and produced these dark plains that we see.
And we think that process stopped mostly about 1 billion years ago, But actually, there's been some evidence that suggests that volcanism was ongoing on the moon until about 50 million years ago in kind of small pockets.
Which is really recent, no?
Yeah.
50 million years ago is not that long ago. So the dinosaurs had only just been extinct by then, right? But the mare is mostly located, as I said, on the side of the moon that's facing us. So on the other side, which dominates, is the highlands, which are all these light spots.
And these highlands are made from a rock called anorthosite, which has a lot of the mineral anorthite in it, which is a calcium-rich plagioclase.
If you look at plagioclase, what the moon's made out of, and indeed a lot of the rocks on Earth are made out of, if you look at plagioclase under a microscope, it looks like a series of black and white stripes, like a zebra, a zebra's skin.
That's called twinning, right?
It's called twinning. You're absolutely right, Mark. And actually, Mark and I met looking at plagioclase through a microscope. We weren't showing them. It wasn't one eye in,
one eye each. So this anorthosite is particularly interesting because the Indian Space Agency sent a mission to the south pole of the moon recently called Chandrayaan-3, and it landed on the south pole of the moon in August 2023. And they were particularly looking for this anorthosite, a particular type called Faroan anorthosite, and to try and work out kind of what was happening when the moon was forming and when its surface was forming. So, it formed soon after we had this impact event and it was cooling. And what we think happened was that there was kind of crystal segregation. So the lighter, less dense crystals floated to the surface, things like plagioclase, and the more dense ones sunk to the bottom of this initial magma ocean that we had covering the entire surface because it was very hot in that early point. And actually, this anorthosite, we think, covers about 80% of the lunar surface. And if you look up at the moon, you can see these darker patches and the lighter patches. Now, Chandrayaan-3 was equipped with an alpha particle X-ray spectrometer, which...
Can you explain in really in-depth detail exactly how that works and the general theory behind an alpha spectrometer?
I'm so glad you asked. We'll save that for another episode. Basically, what you're doing is you're exciting atoms, so you're putting them to higher energy states, and then when they de-excite, they release X-rays, and you can measure these X-rays to look at the types of elements that are present in these rocks. And what they found is that the rocks at the south pole of the moon are geochemically very, very similar to the rocks that we have in the equatorial regions, which is kind of closer to where we've been with the Apollo missions, and we got rocks back from them. And this is important because this supports the theory that we had a global... Can you call it global if it's on the moon?
Sure.
Let's go with it. A global lunar magma ocean. So we had this entire ocean that was kind of forming roughly in the similar way by this crystal segregation, lighter things kind of rising to the top. And this has been published very recently in Nature by Vadawale et al. In 2024. So, an important finding that's starting to kind of differentiate between these processes.
So it was always hypothesized that the moon was once this molten ocean, but this is confirming that?
Yeah, and it's more what were the kind of the dynamics of that system as it cooled down. So there are other options as well. So the alternative hypothesis is something called serial magmatism, which was put forward in the early 80s by David Walker in 1983, a paper, and then Longhi and Ashwell in 1985. And basically what this hypothesis says is that you have this magma ocean, and as it cools, it starts to get slushy, a bit like a slush puppy. And you get these crystals that start to form within this magma ocean. But because it's so slushy, you don't get this segregation into the lighter, less dense things floating to the top and the heavier stuff sinking to the bottom because it's so slushy. So crystal segregation is actually quite difficult in this kind of convecting ocean, particularly because the moon's smaller, the gravity is much lower, so you can't get that separation.
Just to reiterate, when molten ocean started to crystallize, the denser crystals, things like olivine and pyroxene, sank, right? But the lighter minerals like plagioclase started to float.
Yeah.
And that's why the crust of the moon is dominated by this plagioclase, which produces anorthosite.
Yeah, exactly.
And that's abundant in the lunar highlands.
Yeah.
Okay.
So that fits really nicely with this kind of crystal segregation in the magma ocean. But in this other option, the serial magnetism, what we're saying is that it's harder to get that segregation of the different densities of crystals. But what probably happened is that as this slush puppy of a moon started to kind of crystallize more stuff as it cooled, it reached a critical threshold of crystal content. So you had loads of crystals, and this happened particularly at the surface, I imagine, because it's cooler at the surface, you can lose more heat. And so what this did was it formed a crystal-rich lid and then a hot interior. And then what you got with that is that you had magma chambers underneath that lid, creating sort of geochemical diversity throughout the moon through this hotter interior. And you got repeated intrusions, so this magma moving up into the lid. And in this case, you would probably expect to see across the moon's surface slightly different geochemical signatures, because you've got different pockets of magma coming up from underneath the surface and feeding up into the crust. Even, it might still be forming a northocite. It was, because we know there's a northocite in the crust, so that has to be the end goal that we tick. And actually, even in this kind of convecting slurry, there was still a bit of density kind of processes operating here, where the lighter, a northite enriched melt in the lid itself was able to kind of rise to the surface. So you might expect kind of some heterogeneity laterally as these pockets of magma were rising up, still forming northocite, but like the trace elements, so maybe things like scandium or cerium, they're called rare earth elements. They might be slightly different, but actually what this study from the Chandrayaan-3 mission is suggesting is that they are very, very similar to the rocks at the equator, and so it's probably all formed from a lunar magma ocean.
And I suppose the next stage of the research is to collect more samples, or because that's very difficult to do? Or is it to conduct more to get a better picture of the distribution of the magma ocean?
Yeah, I guess you kind of want as much coverage as possible. So this mission landed near the South Pole Aitken Basin, which is 2,500 kilometers across. They think made by a massive impact. It landed about 350 kilometers away from this crater. So, they've looked at this region, but it'd be great to go to other regions, maybe the North Pole. A lot of the Chinese missions, the Chang'e missions, are going to the far side of the moon. Because, as you were saying, we've got more of the highlands on the far side, and we want to know why. Why was there more volcanism on the north side?
It's very hard to it's very hard to see it, at least from Earth, because it is on the far side, and we only ever see the same side.
Yeah.
And I want to talk about that just for a second, because because we only see one side, it almost implies that the moon doesn't rotate, or at least we're tidally locked. But in fact, the moon does rotate. And the way in which it does that is by synchronous rotation. So the moon revolves around the Earth every 27.3 days. It takes approximately the same amount of time to complete a full rotation on its axis. And because those periods are equal, it means that we're only seeing the same side of the moon as it rotates around the Earth.
This is a bit tricky to get your head around, but imagine that you're in the garden and there's a pole, and that pole is the Earth and you are the moon. If you always face the same direction, say you're facing the back of the garden, as you walk around that pole, at some point the pole will see your back, and then at another point the pole will see your front and your face. And that's because you're not rotating. So that's the scenario where the moon doesn't rotate, and in that scenario we would see the back and the front. Whereas if you rotate as you move around that pole, you are orbiting that pole, but you are also rotating your body. And your front if you're facing that pole, your front will always point towards that pole. And what we're saying is the time it takes for you to walk around that pole equals the time that it takes for you to spin around completely. So if you just think about yourself as you walk around that pole, you are effectively spinning on the spot, but you're also moving while you're spinning. And so for each, you move a few centimeters forward, you also rotate a few centimeters. And then you move a few more centimeters, you also rotate a few centimeters. Yeah. So that's why we have a near and a far side of the moon. Bit tricky to get your head around.
That was a really nice analogy, because I struggled to get my head around it as well.
Shall we move on to what in the world?
Yes, please, because I have no idea what's coming up here.
So, the Romans invaded the British Isles, right? in the early AD. So Caesar came in 55, 54 BC, and then Agricola and Hadrian came back in the kind of early hundreds.
They set up Londinium.
Yeah, exactly. Yeah. And they encountered the Picts. And the Picts didn't call... So the Picts were in Scotland. They didn't call themselves the Picts. The Romans called them Picts because Picts means painted people, like picture. Because they'd put like war paint on. And the Picts were very good at guerrilla warfare. So the Romans actually stopped at the Caledonian border because they didn't want to go any further. They couldn't really beat the Picts. And what the Romans found, that basically the point where they couldn't get any further, they built a load of forts along this jutting cliff that pretty much extends across the whole of that border. And what that was a shelf of dolerite forming a natural barrier and forming loads of crags and scarps as well. So dolerite is a mafic rock, got lots of iron and magnesium in it. It's crystalline, subvolcanic, so forms in kind of shallow volcanoes. And it's got lots of plagioclase and pyroxene in it as well. And this shelf of dolerite formed during something called the Wind-Sill Swarm, which formed in the Permian period about 300 million years ago. And this Wind-Sill Swarm, so a sill is like an intrusion of magma, so that's magma moving into somewhere in kind of a horizontal shape under the ground. And the amount of magma that was kind of produced or that swarmed at this point, 215 kilometers cubed of magma.
Gosh.
One cement mixer is 10 meters cubed, so you'd need 21.5 billion cement mixers.
Wow.
And this Wind-Sill Swarm also formed the Farne Islands, Lindisfarne, where you've got the Holy Island Dyke, Bamber Castle, Dunstable Castle, High Force in Teesdale, kind of this string of really hard rocks, and one of the sills in this swarm. So you had various intrusions, but the main one was the Great Wind-Sill, and this is on average 30 meters thick. So imagine that 30-meter thick kind of slab of magma, and at its maximum, we think it's 81 meters at West Allendale. And the word "win" just means it's difficult to shape and it's black. So that's probably why it's formed these kind of jutting cliffs. It doesn't get weathered out particularly easily. And it caused regional metamorphism of nearby limestones up to 30 meters above and below. So this material was so hot, it was kind of changing the rocks around it.
So just to have context there, when like a igneous rock travels through the crust or travels through sedimentary rock, for example, it sort of bakes the sedimentary rock around it like a cake. And, for every small meter wide igneous intrusion, you might get sort of 30 centimeters of like little baked margin is what it's called. But here we're talking 30 meters either side. Is that right?
Yeah.
30 meters either side of cooked sedimentary rock, either side of this intrusion. That is a whopping intrusion.
Yeah, absolutely
Really
massive. And so it formed this great kind of natural barrier between the Picts and the Romans. And so they built a wall on top of it, mostly made from Carboniferous sandstone, actually, which is an older rock, probably because the dolerite was so hard to kind of chip into blocks. And Hadrian came to the British Isles in 120 AD, fortified the ridge, built his wall, which is 135 kilometres coast to coast. A bit later on, they tried to build another wall a bit further into Scotland called the Antonine Wall, 160 kilometres further north at the narrowest point where it's only 63 kilometres wide, but that one was abandoned. And they think the fall of Britain was maybe due to some bribery on the wall, or the reason the Romans retreated from the British Isles. People got bribes, and then the Picts and locals got in and plundered and pillaged.
You can walk along the Hadrian's Wall. Obviously, a lot of friends have done it from Britain. But anyone listening far afield, then go visit Hadrian's Wall. It's fantastic. It's a great walk. It's great. It's a great week out. It is. You've got a few thousand years of history on the surface, and then 300 million year history under the surface. It's a lot of history to get your teeth sunk into.
Look at us dipping into culture again.
Romans again.
Yeah.
Seems to be a thing, doesn't it? Super duper.
Fantastic. Thank you so much for tuning in, everyone, and we look forward to seeing you next time.
Hugs. Bye.
Bye.